So we have positivity and definiteness. We also want this inner product to have additivity in the first slot, and by that we mean if we now have three vectors and we add u and v in the first slot and inner product that sum with a new vector w, then we want the inner product to be such that the u plus v in the first slot is actually going to be the inner product of uw plus the inner product of vw in for all of those vectors u, v, and w in the vector space V. So it basically just sort of slides right through in the first slot. Homogeneity. Is also something that we want. And this actually will depend on what's happening in the first slot, meaning if we scale the first vector in our inner product, that scalar can slide outside the inner product. That's not going to be true if that scalar is scaling the second slot, but we'll show what happens there in a minute. But here, homogeneity in the first slot is what we want, and this is true for all scalars and for v and w vectors in the vector space V. Then we want our inner product to have conjugate symmetry, which now means that if you look at changing the order of those vectors in the inner product, then you're actually looking at taking the complex conjugate of the changed order of those vectors, meaning this is now VW is equal to WV inner product complex conjugate of the result, or of that scalar. So if you change the order, now they're related by a complex conjugate. Question? So now we're assuming that for this conjugate symmetry, if we need a conjugate, then we have it. If our field of numbers that we're playing on doesn't have this conjugate, for the reals, this simplifies. So if we had another field, then you would have to see if it makes sense on that field if a complex conjugate exists. If it doesn't, then you simply can have VW's inner product being equal to the inner product of WV. So it's symmetric. But if you're dealing with something where the field has complex conjugates, then you need to invoke this conjugate symmetry. Yes? So we will start to see where that helps us or keeps us sort of honest relative to this now forces particular relationships in the way that we define our inner product. We need our inner products to satisfy this conjugate symmetry. So if we switch the order, then we have to define our inner product such that this conjugate symmetry relationship is true or holds. So now the question is a good question. If you now took V with itself, you want that to now be a non-negative number. So that non-negative number is a real value, meaning if your vectors were complex, and depending on how you've defined your inner product, if you weren't conjugating things in the definition of your inner product, you could end up with sort of complex numbers coming out of your inner product, and that's not what you want in terms of satisfying this positivity relationship. This is greater than or equal to 0. So hopefully this will start to make a little bit, or we'll feel a little bit more comfortable with it when we look at some examples. So let's now just keep clear that in the textbook they may not use that asterisk. I don't make a very good asterisk anyway, but Axler actually may just use an overbar for the complex conjugate. So when you're reading the textbook, make sure you're clear as to what's actually going on. And sometimes books, when they have vectors, they may put an overbar on it. So don't get confused. Hopefully it's somewhat clear from the context what is happening or what's being used. But here, the overbar is the conjugate in the textbook. And one more comment relative to this complex, or this conjugate symmetry, is that the conjugate symmetry simplifies if our vector space V is in fact a real vector space. And as I've already commented on, here's where this term comes from: an inner product space. So now, more than just a vector space, now it's an inner product space. An inner product space is a vector space, let's say capital V, with the addition of, or plus, an inner product rule on that vector space. And we can start looking at some examples. A very important example is if we now have an n-dimensional vector space, f to the n, where f could be real or complex, f to the n, now that's a vector space. We could turn it into an inner product space with the following inner product. We now take this pair of vectors, an ordered pair. Let's now expand this and say now we have, here are the coordinates of the first vector. This we were just calling V before, but since we know it belongs to f to the n, we know we have n coordinates in that vector. Then we had a w vector, which now is w1, w2, up to w sub n. Here's w. We can now define an inner product by taking each coordinate and forming the product with the first vector and the first coordinate of the second vector complex conjugate. So we have v1 times v1 star, and these are, each of these coordinates are scalars in our field that we're using for f to the n, meaning f or v sub 1 and w sub 1 could be complex scalars, or they could be real scalars. If they're real scalars, the conjugate falls apart, or it just trivializes. But now we have v1 w1 star plus v2 w2 star, etc., plus v sub n w sub n star. And this is actually the Euclidean inner product. And if we use that rule for the inner product, then we actually have that if we take the inner product of v with itself, that's actually just the 2 norm of our vector v squared. And here now is the squared Euclidean length of that vector v. And if we specialize that to if our vector space v is in fact restricted to being the real n-dimensional space, then we can actually think of u and v, which are vectors, are just u dotted with v, where this is now the traditional dot product, where u and v are vectors that are n-dimensional. And this is the standard behavior that we would expect if we were dealing with geometric vector spaces. So that's sort of the default picture in terms of how do we create, or what is an inner product. There is one where we simply take this pairwise product of similar coordinates in the two vectors. It's just we have to make sure that the second vector, we perform the complex conjugate on those coordinates when we form the pairwise product of terms. But we also have other possible inner products. And this is where it gets, I think, a little bit more interesting or fun, depending on how you want to look at it. Well, let me not do that. Let me say other inner products are possible. Let's say now the first one that we will look at is we can define another inner product on f to the n. We don't have to just have this pairwise product. We could actually scale those pairwise products. Meaning, we could, for the w inner product, that could be c1 v1 w1 star plus c sub 2 v sub 2 w sub 2 star, etc., down to c sub n v sub n W sub n star with the C sub i's coming to us from the set of positive real numbers. As long as we keep these C's, these weightings, so now we have a weighted pairwise product of coordinates in our two vectors v and w. That's on f to the n. We could think about having an inner product on polynomials. And here these are the mth order polynomials. One such inner product would be if you had a polynomial p and a polynomial q, you could now take the integral from 0 to 1 of p of x and the complex conjugate of q of x, integrate those from 0 to 1, and that now forms an inner product on p sub m of f. If we specialized m, little m, to be second order, let's say on p sub 2, and let's restrict our coefficients to be real, then we could actually say that, well, one inner product of v and w is the following. Let's now find or evaluate polynomial v at a certain location on the real line. Let's say that we now say, oh, let's take v at -1 and multiply that by w of -1 and add that to another point of v and w, v of 0, w of 0, plus v of 1, w of 1. Let's look at a question. Pardon? Yes, so this could be negative for an arbitrary v and w. But now if you have this with itself, the positivity is when you have the vector with itself. So you're correct, an inner product can be negative. So that's where we want to make sure we're not getting too focused on some of these properties. But yes, it should still be satisfying all of those properties that we defined to begin with. So if we looked at v inner product with itself, now we're simply squaring v at these 3 points on the real line. And since we're dealing with real coefficients, all of those evaluated polynomial values at -1, 0, and 1 can only assume negative, 0, or positive values. And if you multiply 2 negatives, you get a positive. So we're okay with the positivity piece. Let's look at a particular example. Suppose that we have v of t being t plus 1. So now I've changed up x. Now my real number is parameterized by t. And the second vector, w of t, let's say is t squared minus 1. Those are both belonging to second-order polynomials, the set of second-order polynomials, which forms a vector space. And now let's just sort of build this up. V of -1. Now these are difficult problems to do, but it's a late Wednesday afternoon, so we don't want it to be too challenging. This evaluates to what value? That one's 0, isn't it? Then we have v of 0 being 1, and v of 1 is 2. Then we can, knowing how we've defined that inner product, let's now evaluate w at those same locations. W of -1, 0, w of 0 minus 1, and w of 1, 0 again, isn't it? With this definition in the green of an inner product for those two polynomials that belong to the second order, the set or the vector space of second order polynomials, then the inner product of v with w now becomes 0 times 0 plus 1 times minus 1 plus 2 times 0, and in fact that inner product is negative for those two vectors, t plus 1 and the vector t squared minus 1. Those are vectors belonging to this vector space of second order polynomials. Now you may sort of pay attention to the actual way that we define that inner product. It was actually important that we had three pieces or three samples of each of those polynomials to define the inner product. Otherwise, we wouldn't be enjoying this definiteness property. We could maybe have things go to 0 when the vectors themselves are not the 0 vector. But for a second order polynomial, we need 3 values or samples in P sub 2 of R to define an inner product. Meaning, if we now go to the vector space of fourth order polynomials, what do you think we need to do in terms of the number of samples in our inner product? Now we need 5, don't we? So this one now we need, or we would need, to sample the vector at 5 or more values, and then perform this pairwise product and sum. And then, let's say, take the inner product of those 5 values, or the sum of the pairwise product of those 5 values of your vector. Let's look at those two vectors again. Let's say we now have v of t again is t plus 1. Is that what it was before? Yes, okay. So it's t plus 1, and w of t is, let's say, t squared minus 1. But now let's use a different inner product. Suppose now we have v and w, and now suppose we do the integral from 0 to 1. We go the integral from 0 to 1, and this is now v times the conjugate of w, but if we're on the real, or in the set of real second order polynomials, we now have t plus 1 times the complex conjugate of w, which is t squared minus 1 dt. And this is why you spend a semester in calculus learning how to integrate. First, we now have to form the product, which isn't too bad with these polynomials. We now have t cubed, let's say, minus t plus t squared minus 1 dt. Or we now have 1/4 t to the 4th minus, maybe I'll change the order here, plus 1/3 t cubed minus 1/2 t squared minus t, so that I have my orders of t in the right descending manner, and then I evaluate that at the upper limit and subtract the lower limit. The lower limit, I'll do that. That's pretty easy. The upper limit's not that hard either. We now have 1/4 plus 1/3 minus 1/2 minus 1, which if we combine 1/4 and 1/2 in the algebraic way, we have minus 1/4, and the 1/3 minus 1 is now minus 2/3. I can get a common denominator, and now I have minus 3, and 2/3 of 12 is 8. So that particular inner product produces, for that same pair of vectors in the same ordered way, minus 11/12, and what was it using the other? Minus 1. So they both gave us a negative value for the inner product, but we didn't have to have the same numerical value for the inner product. One thing that we can maybe observe is, notice that this first slot actually exhibits additivity and homogeneity. And because of that, if we fixed the vector in the second slot, we would then have a linear map for all vectors in the vector space. Thus, for a fixed W, or a fixed vector W, then we know that V W, and now we fixed W, no matter what we pick for V, we use the same W, is now a linear map from the vector space V into the field of numbers F. So if somebody wanted a linear map, they could create one by just using an inner product and specifying the vector in the second slot. If we play a little bit more with what's going on in the second slot, let's look at what might happen with respect to additivity and homogeneity. Is it the same as what we had before in the first slot? We can also prove or show certain properties write that as a number about the second slot. What happens to additivity in the second slot? Suppose now we just say, let's start with a vector U and take the inner product of that with this sum of vectors V and W. Well, we can put this V plus W into the first slot in what way? By conjugating that. So if we change the order of these two vectors, the first slot and the second slot vectors, then we need to take the complex conjugate of that interchanged order, inner product. But we can do the complex conjugate at the very end. So let's pull that out, and now we have just this additivity of the first slot, meaning now we can use our additivity of the first slot to produce VU plus WU. And we can conjugate that, but the complex conjugate could be applied to both of those pieces separately, so that now we have VU complex conjugate plus WU complex conjugate. But we can get rid of the complex conjugate by reversing the order again. And now we have UV plus WU. And what have we learned? Now we have, if you look back at the very first expression, we really have additivity in the second slot, just like we had additivity in the first slot by definition. So now, if you have two vectors added in the second slot, you can simply pull that apart and have two inner products. What am I doing? Wake me up. I'm seeing these, and I don't even have my glasses on, and I could still see the faces scrunching or wincing at what I just wrote down. Does that look a little bit better? That should be consistent now, maybe, if I could look at the board. Is that better? I was just making sure you guys were awake. I know I'm not. I'm sleeping up here, but I guess that's allowed if I don't make too many more mistakes. Let's now look at the conjugate homogeneity in the second slot, or what's happening to the homogeneity property in the second slot. We are actually going to see that that scalar needs to be conjugated when we slide it out in front of the inner product. So we'll call that the conjugate homogeneity in the second slot. Meaning, if somebody now gives you a scaled second slot vector and the scalar is A, then we can move that scalar into the first slot because that's where we know how to treat it. But in order to move it into the first slot, we have to conjugate the inner product. Meaning now, if I can stay awake long enough, we have AV comma U conjugated. But again, we can play with that conjugate, holding that off until the very end, and we know how to treat this inner product of AV comma U when we have a scaled first slot. That's the homogeneity of the first slot. So that we can now say that's A VU conjugated. But we have two scalars. The complex conjugate of the product is the product of the complex conjugates, so that we can now say that this is A conjugated VU conjugated, but now we can get rid of that conjugate on the inner product, and we now have A complex conjugate UV, and now we can see why we titled that the conjugate homogeneity in the second slot. If you have a scaled second slot vector and you don't want that scaling in your inner product, you can slide it out, but you have to conjugate it, unlike if you had the scaled first slot vector. Now that we have these inner products, we've already compared one of those to the square of the Euclidean 2 norm, we can start generalizing this a little bit. Let's talk a little bit about norms. And we have discussed these different norms. We had a 1 norm, a 2 norm, a 3 norm, an infinity norm. So we've discussed various norms. Not all of these norms let's say play nicely with this notion of inner products or with inner products. Let's just, though, from here on out, we're going to define the norm as, let's say, the norm of V is now going to equal the square root of the inner product of V with itself. That's just how we'll define a norm. So we could have many different norms depending on what the inner product is that we've used or that we're using. Note that if this inner product is the Euclidean inner product, then this is in fact equivalent to our earlier definition of the 2 norm. But if we don't use the Euclidean inner product, then this norm can be pretty much anything. However, we'll use this definition, which means the norm is equal to the square root of the inner product of the vector with itself. We'll use this definition with any inner product. And one result that you can show is that if you scale the vector you scale the vector V with a scalar A, and you look at the norm squared, that's the same as taking the absolute value of A, whatever your scalar was, and squaring that, and multiplying by the square of your norm, of the original vector V. Now that we have this inner product, we've learned that sometimes we could possibly have this inner product equaling 0, and that's now going to be allowing us to use the terminology orthogonal. So let's now talk about orthogonality now that we have the ability to go from 2 vectors down to a scalar, and in particular that scalar could be 0. 2 vectors say V and W, that are in the vector space V, are orthogonal if the inner product of VW is equal to 0. I hope you can see that that also implies that WV is also 0. What can we say about the 0 vector and orthogonality? Which vectors are orthogonal to the 0 vector? All of them. So the 0 vector is orthogonal to every vector and 0 is the only vector that is orthogonal to what? To itself. All the others are going to give us some non-negative value. Let's now look at orthogonality, not just in the traditional vector sense. Let's look at an example where our vector space, again, is this second-order polynomials with real coefficients, or over the real number line. And let's go ahead and use the inner product that we had defined earlier. Let's say V and W, the inner product, is going to be V minus 1, W minus 1, V0, W of 0, plus V1, W of 1. And suppose somebody says, okay, there's an inner product. You're playing with the vector space of second-order polynomials over the real line. Find a vector W that is orthogonal with the above inner product of those three terms, or values of the vectors at -1, 0, and 1, the sum of pairwise products of those values. And let's find a W that's orthogonal to a V of t that's equal to t plus 1. How might we go about finding such a W? What would you think or guess? Yes. Do you have more than one W? Yes, so now you want these two vectors, V of t and W of t, such that these pairwise products at these 3 points sum to 0. So now you know what t plus 1 is, but t plus 1, I'm seeing somebody maybe drawing a line in the air. Is that now this straight line with intercept of 1 and an angle of, I'm sorry, and a slope of 1. And so now you're just thinking traditionally, aren't we? But now let's say that we can have more than just straight lines. We're in the vector space of second-order polynomials. Let's now just pick some arbitrary w with some unknown coefficients and see if we can find several such w's that will provide us with this inner product being 0. Meaning, suppose that we just let w of t be something that's yet to be defined. Let's say we have alpha is yet to be determined times t squared plus beta t plus gamma. And now we can evaluate that w at the 3 different points. W of minus 1 is going to be alpha minus beta plus gamma. W of 0 will be gamma. And W of 1 is now alpha plus beta plus gamma. And the corresponding v's, since v is specified, we have v of minus 1, that's 0. V of 0 is 1, and v of 1 is 2. And we actually need the inner product of v and w to be 0. Or we can take v of minus 1, which is 0, and multiply that by alpha minus beta plus gamma, plus 1 times gamma, plus 2 times alpha plus beta plus gamma. And we want that to be equal to 0. First piece goes away nicely, or fortunately for us, and now we just have 2 alpha plus 2 beta plus 2 gamma plus 1 more gamma. Or we have 2 alpha plus 2 beta plus 3 gamma equaling 0. And all we really need to do is pick alpha, beta, and gamma to satisfy that condition, and we have orthogonality of this w with v, with that particular v of t plus 1. And I think you can now see that we have all sorts of possibilities. We have 3 variables and 1 equation. For example, we could simply let alpha be 0, and now we've reduced the order of that polynomial w. Now it's no longer a second-order polynomial. Now it's a first-order or less. This now says that we have 2 beta plus 3 gamma equaling 0. If we pick gamma equal to 2, then beta is going to be minus 3. Or we now have, let's say, a w sub 1 of t of beta t plus gamma, and that's going to be orthogonal to v of t equal to t plus 1 with the chosen inner product. And maybe that's not what you were directing before with your hands, as far as maybe I wouldn't have guessed that particular choice, minus 3t plus 2 being orthogonal. What are some others? Suppose that we now pick a different one of those three coefficients to be 0. Suppose we let gamma be 0. Now we have 2 alpha plus 2 beta equaling 0, or alpha is equal to minus beta. If we let alpha, the leading coefficient, be 1, maybe, then we have the next coefficient being its negative, or minus 1, and now we have a second polynomial, w sub 2, is alpha times t squared plus beta t, or that's t times t minus 1. That polynomial now is also orthogonal. To t plus 1. And we could check that if we wanted to. V of minus 1 was 0, V of 0 is 1, V of 1 is 2, W of minus 1 is what? That's now minus 1 times minus 2, or 2. W of 0, 0, W of 1, 0. And now if we simply sort of do that pairwise or take the sum of the pairwise product, we now have 0 times 2 plus 1 times 0 plus 2 times 0. Zeros are wild. We now have 0 for that. Yes? So now the question was, since these are polynomials, why aren't we doing the integral for our inner product? We could, but we're showing that we can have different kinds of inner products, and this one might be easier than your calculus-based inner product. So now maybe you go, I never did like calculus. Now I can pick an inner product that doesn't need calculus. I can simply select, if it's a second-order polynomial, I can pick 3 locations on the real line, evaluate my vector at those 3, and form an inner product with that. Or I could say, oh, I just want to get kind of crazy. Let me pick 5 points, and I'm still on a second order. That's okay. You could evaluate that at 5, and now you have this sum of 5 points, but maybe you're making your problem more difficult. It's not critical that we use that integral. We could use this inner product as long as, what do we need the inner product to do? It needs to satisfy those properties that we began with. But as long as what we select satisfies those properties, then the inner products are not going to be equivalent, but they should give us consistent results or consistent information. That's correct. So the inner products are definitely not going to give you the same numerical value, and we saw that earlier when, wasn't it negative 11/12 and minus 1? We did the integral one way, and or maybe I'm getting my numbers wrong. Let me, minus 11/12, and that was based on the integral. And the other approach gave us minus 1. So the product, so here the question was, how come the inner product of VW is not equal to the inner product of VW? It's clear from the context. No, you have to be told. This is another one of those situations where you have to know what that inner product, what the bracket, the angled bracket means. You have to say angle bracket VW is defined to be, and then you have to state what the inner product is. And now that you've stated that, now whatever you're doing, you have to live with that inner product. So you can't say that this inner product is equal to that inner product. So if you wanted to, you could label them. You could get your 64 colors out and say green inner product is not the same as blue inner product. You just have to know which one is which. So you now assign what you want for that inner product and then use that in whatever way we're wanting to play with it. So, with that said, let's look at generalizing the Pythagorean theorem. This is now 6.3 in Chapter 6. If we have two vectors, u and v, then those two vectors are orthogonal, or if u and v are orthogonal vectors in V. And now being orthogonal is going to depend on the inner product, and we haven't said anything about what the particular inner product is, but if u and v are orthogonal vectors in V, then the norm of u plus v squared is equal to the norm of u squared plus the norm of v squared. And we didn't say anything about the inner product. We just said if we have an inner product that allows u and v to be orthogonal, then we know this relationship on their norms is true. And how are we defining the norms? Using the inner product that we've agreed that we're using that produced orthogonality. And the proof is one that you wished was on exam number 2. Meaning, if we start with u plus v, the norm of that squared, how did we define the norm squared? That was simply the inner product of the vector, wasn't it, with itself. So in this case, we have the inner product of u plus v with the inner product of u plus v. But we know how the additivity of the first slot, what that produces. That now just sort of breaks that up into two pieces, or two inner products. We can now say u plus v plus v u plus v. Make sure I stay awake. Now what do we do? Well, we've just shown what the additivity of the second slot allows us to do. It again separates this into each one of these into two different parts, meaning we can now rewrite this as u plus u v's inner product. That's from the first one because of additivity of the second slot, plus vu plus vv. But now I can actually rewrite these inner products with themselves as norms squared, meaning I can now say this is u, or the norm of u squared, plus the inner product of u and v, plus the inner product of v and u, plus the norm of v squared. But remember what we were assuming as a hypothesis in this theorem. They're orthogonal. We didn't say what the inner product was, but we know they're orthogonal, and so if they're orthogonal, that tells us what this inner product is. Now we know that this is 0, this is 0 by hypothesis, so that we now have the norm squared of u plus v, or the sum of u plus v's norm squared, is equal to the norm of u squared plus the norm of v squared under what condition? As long as u and v, those vectors, are orthogonal in the vector space. And orthogonality is going to depend on how we've defined our inner product. And that's one of the key ideas to sort of draw from this theorem. Note, this did not depend, I should say this result, did not depend on the specific or the particular inner product that we were using. So whatever we pick for the inner product, our norm definition actually changes along with the inner product definition. And we didn't specify, although this is how we grew up with the Pythagorean theorem, we grew up with it on the plane, didn't we, in R2. We didn't specify that our vector space V was in fact R2. We didn't require that. Now we have this generalized idea. We could be in a in a five-dimensional space, vector space, and we still have this nice property of Pythagorean theorem. That now allows us to use, or actually talk about, orthogonal decomposition. Meaning we want to break up a vector into two parts. If we're given two vectors, let's say u and v in our vector space V, we want to see if it's possible, how can we write u in terms of v and a vector perpendicular or orthogonal to v. We want to break u up into two parts, one in the direction of v and one that's orthogonal to v. That's how we would like to rewrite u. We would like to decompose u into two parts, one that's in the direction of v and one that's orthogonal to v. Now to see that, or to do that, let's just pick a scalar, a, that's yet to be defined, but it's in our field of numbers. Now what we want to do is just play a little bit fast and loose with how we write this vector u. Suppose u is now some scalar multiple of v and some vector that's orthogonal to that. But if u is on the left, u has to be on the right. Well, we can make u be on the right if we say, well, this is u minus AV. I haven't changed anything. I've just added 0. I've added the 0 vector. But now I have a component of u that's in the direction of v, and I have a component that I hope is in the orthogonal direction. The thing that I haven't yet done is I haven't said what A is. So A, we want to pick such that AV, that's in the direction of V, is orthogonal to U minus AV. Think about that over the weekend while you're doing homework 4, maybe homework 5, and we'll figure out how we assign or how we define this scalar A so that this decomposition is an orthogonal decomposition. We have a piece of U that's in the direction of V, and the other piece is in an orthogonal direction to V, just by the choice of A. And we can do that with our knowledge that we already have, the Pythagorean theorem and inner product.